All right, let's get started. All right, so problem set's due. It will be coming out. Any questions or problems about anything? All right, so we were looking at minimum edit distance at the end of class last time, so we'll return there. And as you recall, we decided that the way we would approach the problem is by characterizing the number of edits, the minimum number of edits it takes to convert the first n characters of a string R into the first n characters of a string S. And then, of course, the overall solution being when these two numbers equal the total length of the string. And this is what we came up with, these base cases here. Say what to do when what the number of edits is when one or the other of the strings is empty. And in these two recursive cases, this one applies when the last characters of the substring are equal, and the second one applies when they're not equal. So you can view this in two ways. You can view this as the skeleton of a recursive function, where E is the function and here's some recursive calls. Or you can view it as rules for filling in an array, where it says the elements of this array element depends on these array elements. And either way is fine. And then we went through the process of systematically filling out this array. And what we saw is that we want to, we deal with the base cases first. So we fill in the first row and the first column according to those base cases. And then it's just a matter of going through and filling in each box according to these two rules right here. We use this rule when the box is yellow because that is when corresponding letters are the same. And the non-yellow boxes we use this more complicated rule, where we have to choose between three edits. And the bottom line is you just go fill it out row by row. And after I ended class last time, at least two people came up and asked me, well, what's the answer? Where do you find the answer to the overall problem of turning snowy into sunny? So where is the answer? How do you extract the answer to the original problem from this? Yeah?
It's the number in the top right column.
Right, it's the number in the top right column. That number tells us the minimum number of edits it takes to turn the first 5 letters of snowy into the first 5 letters of sunny, which is to say all of those strings. Now, we talked about the optimal substructure property. And you can see the optimal substructure property exhibited here, in that the solution to every subproblem is in that array as well. So what's the minimum number of edits it takes to convert the first 2 characters of snowy into the first 3 characters of sunny? You just come here, come up here, that's 1. So you can read the answer to any of the problems out there. So that's basically where we stood at the end of class last time. So let me pause and see if there are any questions about this before going on. Okay, now, suppose you had to code it up. There are 2 ways you can do it. You can, correspond to what I just said a minute ago, you can view this as a recursive function definition, or you can view it as array update operations. So let's look. Here is a direct recursive computation. So we want a method that takes in 2 strings, R and S, and computes the minimum edit distance. So I'm going to make use of this helper here, min edit distance. That takes 4 parameters, R and the number of characters of R we care about, and S and the number of characters of S we care about. And initially we care about all of them. And here is that helper function. And look at it, what do you see? Where have you seen that before? Yeah.
That's the same set of instructions we filled the array out with.
Right. That's just the, it's this. It's this stuff here. The only difference is I only have two base cases because really this base case is a special case of both of those. But these two base cases, these two recursive cases, I just carried it forward into the implementation. The two base cases, the two recursive cases. This simple one applies when the characters agree. This three recursive calls applies when the characters don't agree. So it's just a direct implementation of that thing. So once you do what we did on the other slide, this just falls out of it. Now, what's going to happen when we run this on sizable strings? Suppose we ran it on two strings of length 1,000 that have no characters in common. Okay, what's going to happen? Yeah. It's gonna. You start with you got the problem. You got to solve the problem when when you care about the first 1,000 characters of those strings. That'll make 3 recursive calls to the 999 level. Those will they each make 3 recursive calls. Those will all make 3 recursive calls. So it's a disaster. But that's easy to fix as well. You just create a cache. So to the I add another parameter to min edit distance, which is the cache we're going to use. It's a dictionary that maps pairs to ints. Now, why do we want to have pairs as the keys and ints as the value of this cache? Yeah. Okay, so the parameters there are 4 parameters to the method that we're going to cache. 2 of them don't change. R and S are always the same, so we don't need to worry about them. The parameters and values change each time a recursive call is made are this parameter here and this parameter here, which we're using as array indexes. And so it's the pair of them that define a subproblem. So we're going to map unique pairs of this parameter and that parameter to the minimum edit distance that corresponds to it. So we create the cache, and then we change our other method this way. We add the parameter. When we first enter the method, we look up the answer, see if we have the answer saved. If we do, we just return it. Otherwise, when we compute an answer, we cache it, and then we return the cached answer. So it's just pretty simple change to the existing method, really a mechanical change to the existing method. And it makes all the difference. Suddenly, now the complexity is going to be the product of the length of the 2 strings. So if both strings are length n, then we got a n squared alpha. Okay? So, there are degrees of misunderstanding you can have about this. You can be uneasy about where this came from. Okay? You could understand this and not understand that, which would actually be worrisome. I mean, not understanding that's very understandable. Once you see that, seeing that this is really just a direct implementation, that's pretty straightforward. And this part of adding the cache is just purely mechanical. So that's why I keep saying the creative part was coming up with that original idea of defining minimum edges in a particular way and coming up with the recursions. The rest is just mechanical implementation. Okay? Now, I mentioned that you can also view the problem not as making recursive calls, but as just filling in the array the way I did in that animation. What would that code look like? What if you wanted to code it that way? Start with an array and just fill it in instead of having a cache that gets populated as recursions happen. Go back to the picture. Okay? What kind of code would you write to fill in that array right here? Yeah?
Just use a double for loop.
Right, it would just be a double for loop. I mean, look at how I filled it in with the animation. Okay? So we'd have, to set up, we'd have a loop, we'd allocate the array of the right size depending on the length of the strings. Then in the bottom row, I'd write a loop that just fills in the numbers from 0 to 5. Then I'd write a loop that fills in the first column from 0 to 5. And then I write a loop that iterates, lets n iterate in this direction. And m iterate in that direction, or I and j, however you want to do it. And you just fill in this box, this box, this box, and so on, according to these rules. So to fill in this box, you would look at this one, this one, this one, take the min and add 1. And it's just a doubly nested loop that goes and fills in the array. Just like that. That would be an animation of the algorithm, and that's what it looks like. We create the two-dimensional array table. There we are filling in the bottom row. There we are filling in the left row, left column. And then we have the double nested loop. And you can here. They go from 1 up to n. And we've got one of the two cases. Either things are equal. So we do this. We just copy the diagonally adjacent value into table ij. Where they're not equal, in which case we take the min of the 3 elements, add 1. And then when we're all done, there's our answer that we can do. So that's another way to do it. So which is best? Fill in the table explicitly, like this, or write the recursive solution and cache things? Yeah?
Typically the table, because it has better locality and doesn't use many stack frames.
Okay, so we avoid any problem with, if we do it this way, there's no recursion. There's no problem of, with recursion, you can end up with blowing the stack if the recursion gets too deep, although there are other ways to deal with that as well. There are exceptions. We'll see cases where the filling in the table version doesn't work as well, isn't as efficient as the recursive version. But typically, for a lot of applications, the table is just going to be more efficient. It's just tighter. It's a little harder to come up with because you've got to understand the problem well enough to figure out how to represent all the values in an array somehow, or in some data structure. And you got to compute things in the right order, right? You can't start from the upper right and work down. You can't start from the lower right and work in the other direction. You've got to be sure that when you go to fill in an array value, you've already computed it. When you memorize, when you cache a recursive function, you don't have to worry about that. It just works out. Okay? Traditionally, this is what's called dynamic programming. It's setting up a problem to be solved in this form, filling in a table. But in terms of programmer effort, the caching method is easier. It's almost like another step to solve this problem. Okay, so let's we'll go to another set of slides, and this is another problem that I got asked after class last time. After you have filled in the table, how do you recover the solution? In other words, okay, it's 3 edits, but which 3 edits? What 3 edits do you apply to Snowy to turn them into Sunny? So if all you want is the number, that's fine. That may be all you want to know. But if you want to know the full details, you've got some more work to do. And the way you do it is, once you've got all those things computed, start up where the answer is and reconstruct how you computed that number. Okay? So let's just do the following exercise. Why did we write a 3 up there in the upper right-hand corner? Yes?
Because the last letter for the C and
Okay.
the minimum of the options.
Okay, so that we're in a case where the letters agreed in this case. And so we just copied that 3 from the thing diagonally adjacent to it using this rule right here. So if that doesn't correspond, that didn't require an edit operation because the characters are the same. So that's where we start. We copy that number from there. And that, no edit required for that. Now, why did we write a 3, that new 3? Why did we write that 3 right there? Where did the 3 come from? This one right here. Yeah?
Just adding 1 to the minimum of the one
Okay, we took the minimum of these three, which was 2, and added 1. So essentially, each of these numbers corresponds to a different kind of edit. Okay? So we're going to pick one. What we're basically doing is tracing our way back to the beginning. And we took them in, and there are 2 that have a 2. Let's just assume that, let's just pick this arbitrarily as where we came from. Okay? That corresponds to a deletion. So if you go back to where we came up with these 3 operations, one corresponded to deleting a character from R, one corresponded to inserting a character into R, and another corresponded to replacing a character. So each of these cases corresponds to some kind of edit. So what we just did was we figured, okay, when we were figuring out what that 3 was, we took the 2 and added 1 to it. So we were essentially doing one edit. That 1 is an edit. So we figured out what the first edit to do is. Now, why do we write the 2 there? Why do we write this 2 right here? Again, we took the min of these 3 things. That was the min, and we added 1 to it. And that one is this one right here. That's this case right there. And what case was that? How did we derive that case? What kind of edit led to that? Hard to remember. That was a replacement. Right? Now, why do we write this 1 right here? Okay? Because we took them in, it was of these 3, it was a 1, we added 1. So let's say we took this 1 and added 1 to it. Well, I guess I didn't do that. Let's say we took this 1 and added 1 to that. That's our 3rd edit operation, so that will be not a delete, not a replace, but an insert. Oh, I take it back. That was a yellow one, so we just copied up, so that's no edit. Sorry about that. Yeah. Let me go back here. We wrote this one here. That's a yellow box, so the character in and in agree. So we just copied this one up, so there was no edit involved there. Okay. What about here? Why do we write a 1 right here?
0 plus 1.
Because of 0 plus 1. And that is what corresponds to the insert operation. And then finally, we wrote this 0 here because there was a 0 there. So we started at the beginning and worked our way back, started at the end at our answer, or worked our way back to the beginning, reconstructing why we made each choice. And you can see this works now. Let's try it out. So if we have snowy and sunny, so it says delete R3, so 0, 1, 2, 3. So delete the W, that gives you SNOY. Replace R2 with S3, which would make that into an N, and then you'd have SNNY, and then insert at S1 at R1. So we take this U and stick it in, and we have SUNNY. So we can reconstruct the decisions we made, figure out the answer. Now, we had some arbitrary choices. Like right here, I chose to backtrack to that spot. I could have backtracked to that spot. I could have said, what I did was I said, okay, we took this 2 and added 1 to it. I could have said, we took this 2 and added 1 to it. So what would happen if I took different route back to the beginning? Would I get a wrong sequence of edits?
No.
What would I get?
Different sequence.
I get a different sequence of 3 edits. That still work. So there's multiple solutions, multiple ways to do it with 3 edits. All right? Yeah.
When you're deciding what to put in the top right one,
Mm-hmm.
that's the case where Rn minus 1 equals Sn minus 1?
Yeah.
So can you show what Rn minus 1 is and what Sn minus 1 is?
Okay. Well, this is R right here. And this is S right there. So in this case, R and N and M are 5. So this string sub 4, 5 minus 1 is what?
I'm not sure I understand.
Okay. Snowy is a string with length 5. That's R. Sunny is a string of length 5. That's S. Okay? Upper right-hand corner is at index 5, 5. So N is 5, M is 5. You subtract 1 from N, you subtract 1 from 5, you get 4 and 4. And this Snowy sub 4 is right here. And Sunny sub 4 is up there. They're sort of lined up along with these indexes. These indexes belong to the array up there. So it's a little misleading to, looks like maybe this is index 5, but this is index 4 of the string. Yes?
Is there no way that you can get the path as you're constructing it?
All right, okay, good idea. Instead of going back and reconstructing it, why not, when we write the 0 here, just remember, well, I guess there's nothing to remember there, but when we write the 1 right here, just remember we wrote the 1 there because insert. Okay, so associate with each square here, not just a number, but the list of edits that got you to that point. What do you think of that? Would that work? So when you're done, you just got the list of edits computed. Question? Yeah?
It's a way larger space requirement.
Right, it takes a lot more space now. Because before, we just had to store a single integer in each of these boxes. This way, it's an integer plus a list. And the list can be up to n long. Number of edits can be up to n edits. And so you end up with way more space to consume. Because you're essentially, you're storing it not just for the bolded numbers, you're storing it for every single box you compute. So it makes it a lot less space efficient. Yeah?
When we're going back over the edits to reconstruct the solution,
Mhm.
do we assume that the indices change, like after delete? Do we assume that the index just is blank, or do we assume that it's actually
Well,
everything?
because you're working, it would be confusing if you were heading in that direction.
Right.
But the way this is constructed, when you read it down, when you delete index 3, that changes this thing to the index 4.
Okay.
But you never refer back to that index. The index is getting smaller as you go down. So you don't want to read them up or it doesn't work. We're going reverse. All right, so that's nice. What if we don't have a table? What if we use the caching method? Are we out of luck? Can we reconstruct a solution from a cache?
Doesn't hold on to information.
Yeah, it holds exactly the same information. It's just organized in a hash table instead of in an array, but it still has every single one of these key to pairs of indices. So you do exactly the same trick. Now, let me show you potential efficiency. Suppose you did not care about reconstructing the solution, you just wanted the number. How can you do this in less space? This takes two strings of length n, it's going to take n squared space. Yeah.
Do you actually have to fill in the entire array, or can you only fill in the areas that are needed each time you try to compute
Well,
something towards the upper right?
it's a little hard. It'd be nice if we only had to fill in the ones that matter. But it's hard to tell which ones are going to matter if you've done it. There's a simpler way we can save space. Yeah.
Is it possible to know that you're either going to have a no edit or an add one function, so you can just kind of do like a min trail?
No, I mean you could. So look ahead and see these yellow things coming up. You might know there's no need to compute either of these. Well, except this might just have to depend on it. That's not what I had in mind either. Yeah.
Since you're only editing one line at a time, could you just have a few one-dimensional arrays?
Okay, that's it. Think about when you're computing this last row up here. What values in the array does this row depend on?
The ones below it?
Just the ones below it. Once you filled in, say, this row here, row 4, these first rows here, 0 through 3, don't matter at all. You never look at them again, right? You fill in this row, then you fill in this row, then you could throw the first row away. You don't need it anymore. So you could get by with just 2 one-dimensional arrays. The one one array is the one that you're currently computing, and one row is the row you previously computed. Then when you're done, The row you previously, the row you just computed becomes the previous row, and now you compute a new row. So you end up just needing linear space in that case. What about with the recursion though, with the caching? There's no easy way to do that. And so this is a case where if you, if all you care about is that number in the upper right hand corner, with the table-driven method, you can do it in linear space. With the recursive caching method, it's going to take quadratic space. So the table is a clear winner in this case. Okay. Let's look at a different problem. So when we were talking about what search problems were, what optimization problems are, we talked about the knapsack problem. Let me just remind you. Imagine a thief that has a knapsack and can carry it away at most W pounds. So the knapsack has a capacity, and there are a bunch of items in a vault of type A, B, and C. They each have a weight, they each have a value. And the idea is the thief wants to pack as many, you need to pack stuff into the backpack. Can't exceed the capacity of the backpack, wants the maximum value. So we want to find out the best we can do. So this is a famous problem. And I think we even solved these solutions last time, but you've probably forgotten. So if W is 10, what's the best the thief can do? Right, an A and a C gives you 17. What about if you have room for 12? That was 3 B's, $21. What about if you have room for 9? Let's see, we could take 1 B, that's $7. We could take 3 C's, that's $12. 2 C's and a B? Yeah. But what about 2 B's gives you 8. That's, no, I'm reading the wrong theory. 2 B's give you 14, I'm sorry. Yeah, so those 2 B's. So even for the table this small, it's not trivial to look at it and solve it. And you can imagine you have more items and varieties of weights and values. It's kind of tough. So let's see if we can. There's no known greedy algorithm for this. Let's see if we can find a dynamic programming solution for it. Now there are 2 variants to the problem: with and without repetition. So in the with repetition, you can take as many A's as you want, as many B's as you want, as many C's as you want. The without repetition variant, you can just take at most 1 of each item. We'll look at both variants. We'll start with repetition. So if you're going to view this using a greedy algorithm or dynamic programming, you've got to view it as a series of choices. And each choice then leads you to a simpler subproblem to solve. So what are the choices we have to make? What's the choice? We show up with an empty backpack. What's the choice? Yeah?
Take the most expensive item.
Well, I'm going to ask you how to make the choice. I'm asking what is the choice? What do you have to choose? Yeah.
Which coin to add to your bag?
Well, you said which coin, which item to take, right. You choose to take an item of type 3, of type 2, of type 1. Which item do I take? So you choose that item, and now you have your backpack has less capacity because you've taken up part of it, and now you've got another choice to make. So the first choice might be, given I can take 20 pounds worth of stuff, what do I take? And let's say you take something that weighs 7 pounds. Next question is, okay, given that I have 13 pounds of capacity, what item do I take? So that's the choice that you make. If we had a greedy algorithm, we would do something like look at our capacity and look at the available things, do a quick calculation, and just take something and not look back. But there is no greedy algorithm to do this. No one thinks there's a greedy algorithm anyway. So what do we have to do to figure out the best choice? Yeah.
Would it involve just creating all permutations that are less than the capacity?
Well, we're not going to explicitly create all permutations of items. We need to express that in terms of choices. Okay, so there are 3 choices to make here. Since we can't figure out the best choice, what do we do? Yeah.
Because we make 3 choices and 3 recursive calls.
Right.
On smaller.
Right. You say, okay, let's suppose I have 20 items worth of capacity. Okay, so either I got to take an item number 3, in which case I'll have $13 plus room for 13 more pounds of stuff. Or maybe I should take item 2 and then I'll have $7 worth plus 16 pounds of capacity. Or take item 1 and now I've got $4 plus 17 pounds of capacity. And see which one works out best. Try all 3 possibilities. See which works out best. Very similar to the edit problem where we were trying 3 possibilities. So that's just the way it works in dynamic programming. Faced with some choices, just try them all and see which one leads to the best answer. Okay, so let's let KW be the maximum possible value of loot if a backpack has capacity W. That's the best we can do. So what would K of 0 be?
0.
Okay, K of 0 would be 0 because if you can't take anything, you're not going to get any value. So really, and I mentioned this last time, this is a very key step, realizing that we want to define this function that has W as a parameter, because that lets us define the subproblems. You know, what are the subproblems of K of 20? It's K of smaller things. Okay, so K of 0 is 0. What's K of W? How do we find K of W? Again, keep this idea in mind that we're taking 3 choices.
So is it the value of the item you just, you're adding plus K of W minus the value of the item?
Okay, right, exactly. So what he said, well, that's right to a point. He said it's, well, let me just show you what the slide says and trying to wave in the air. So what Prince said was, if you choose item I, then what you're going to end up with, the best you can end up with is the value of item I, plus the best you can do with what's left in your knapsack. W minus the weight of item I. What he didn't say is what's I, and the answer is you try all possible i's. So for each row in that table, you compute this. You take the max, and that's the best you can do. In our case, n is 3, so we're going to be taking the value of item 1, which is 4, plus, let's say little w started out as 20. This expression would be 4 plus k of 17. And the next expression, next I is 2, so it would be 7 plus k of 16, and then we would have 13 plus k of 13. So we would have 3 recursive calls to make. We take the max of all 3, and that's our answer. We try all the possibilities. Now, that sounds like uncontrolled recursion, right?
I can think of worse uncontrolled recursion.
That's true. But what's the bottom line? How many different subproblems are there? If you got to solve k of 20, how many possible subproblems are there?
Times 20.
Yeah, there's just 20, or 21 if you count the 0 case. Right? That's all the subproblems there are, and some of them turn out not to even matter. So yes, it's if you don't use caching, you get lots of recursion, but it's because you're solving the same problems over and over again, so it's right for caching. So let's look at how it works. Again, let's view this as filling in the table problem. We want to compute k of 11. So what I'm going to do is figure out k of 0 and then k of 1 and work my way up to k of 11. So that will correspond to filling in the table. There's also, you can do a recursion and just start at k of 11 and recursively fill in a cache. Okay, so what's k of 0?
0.
We know that. What about k of 1?
0.
Okay, what happened to trying all 3 possibilities and taking a max? There's this little proviso right here that says you can't consider taking an item I if there's not room for it in your pack. So we're gonna keep getting zeros until we get to here, because if all you've got is capacity for 0, 1, or 2 pounds, you can't take anything. So you're not always taking the max of 3 things. You're taking the max of up to 3 things, depending on how much capacity you have. So you get a 0 at 1, a 0 at 2. Now, what's k of 3? pretty definite. So which i's can we work on here?
One.
One.
Right, the only I to consider is 1 because 2 and 3 are still too big to fit into a knapsack of this capacity. So all we're considering is this. We got to take the max of one thing, which is easy. So it's the value of 1, which is 4, plus k of, what's this? 0. So we take 4 and add it to the number in this box, which is 0, and we get 4. Let me write that in. Now the animation shows that the yellow one shows you for each, we're going to highlight for each I that works the value of k of w minus w of I. So that's that, and we write a 4 there. Now, which of the squares does index 4 depend on? Which array index is? We got to decide what to write here at index 4. What does it depend on?
0, 1, and 4.
Depends what's stored here. That corresponds to taking item 2. Because it has a weight of 4, so 4 minus 4, an index, it has a weight of 4, so 4 minus 4 gets you to here. And what's the other one we depend on?
1.
Item 1 is 3 pound sliders. Yeah, so you get there. So it depends on those two. And so we take the max of the first 0 plus $7 and the second 0 plus $4, and that's 7. Okay? What does square 5 depend on? 1 and 2. So we're comparing, for index 1, we're taking the 0 plus $4. For index 1 up there, we're taking 0 plus $4, and we're taking 0 plus $7. So again, it's 7. Exactly. Okay, now what happens here? We're trying to decide what to put in k of 6. And that's going to depend on k of 6 minus 4 and k of 6 minus 3. So what's our answer? Okay, let's take I equals 1. What's the I equals 1 contribution to it? We take an item 1, what will we write in this box? $4 for the value of item 1 plus k of 3, which is $4. So we get an 8. And what if we chose to take an item 2?
You only get 7.
Right, it would be $7 for the item 2 plus $0 for k of 2. So we take the 8, that's better. Now when we finally hit 7, we've got 3 choices to make. Now we're making all our choices. So we take the max of 3 things, and what's it turn out to be? An item 1 would give you 8. An item 2 would give you
11.
oh, I did that wrong. An item 1 would give you 11. An item 2 would give you 11. An item 3 would give you 7.
13.
Where'd the 13 come from?
Wait, it's value 13.
I forgot that. Yeah, we're just taking an item 1. That's 13, right? Okay, thank you. Okay, this box depends this way. So if we take an item 3, that's 0 plus 13 would go here. Or we could take 7 plus 7, which is 14, or 7 plus 4, which is 11. So we get to 14. Okay, this is either 13 or 7 plus 7, which is 14, or 8 plus 4, which is 12. So that's another 14. This one is going to be 7 plus 4, this is 11. It's going to be 8 plus 7, which is 15, or 13 plus 4, which is 17. And finally, I don't even feel like doing it again, but you end up with $20. So your best strategy is to we'll let you steal $20 worth of loot. And if we care to, we could reconstruct while we wrote the 20 there and find out which elements to take by looking back. Okay? So, yeah, it can be, I was a little bit confused. I got turned around trying to fill this thing in. But hopefully you see that makes sense right there. Yeah.
So in the array, you keep the item that's associated with it, so you can go back and like find the next one using the yellow.
Well, you don't have to keep anything other than what's in the array. Okay? So what I'm saying is, if you want to reconstruct the solution, you go here, it has a 20 in it, you say, why did I write a 20 there? And you figure out, okay, I wrote the 20 there because there was a 13 here plus 7. So that's item 2. So I got to the 20 from here by taking item 2. So you take an item 2, and then you go back again, back again, back again. You can just go backwards and figure out what items you had to take to get to that point. Okay? Any other questions? Okay. Now, let's try the knapsack problem without repetition. So now we can only take at most one item. And so here's the key thing. What we have to realize is we're going to define a 2-parameter recursive function, k of w and j. Because we can't, why don't just k of w work anymore? Why can't we define k of w as the best you can do, taking with a knapsack of size w and defining it in terms of simpler kw's? Yeah?
Because all of the recursions depend on previous choices you made.
Well, I said because all the recursions depend on previous choices. Another way to put that is we've got to keep track of whether we've taken an item 3 or an item 2 or an item 1. And so here's the way we'll do it. Whether we keep track of a set of what items we have chosen from, the first choice you're faced with is, should I take an item 3 or not? So you either take an item 3 or you don't. And then the next choice you'll take, after that, you've got another choice to make. Do I take an item 2 or not? And then you choose, do I take an item 1 or not? Those are your choices. So we're going to decide whether to take an item 3 before we decide whether to take an item 2. So we're going to let k of w and j be the maximum possible value of a loop if the backpack has capacity w, as before, and we are restricted to choosing from among items 1 through j, at most one of each. Okay? So you'll see how this works in a second. So what's k of 0 and j? So if you have 0 capacity and you can choose from items 1 through j, what's the best you can do? 0. Now, suppose you have a lot of capacity in your knapsack and you're restricted to choosing items 1 through 0. In other words, you're not allowed to choose any items.
Still 0.
0, right. If you're not able to pick anything, okay. So now this is the recursive case. We're going to define k of w and j. So you're allowed to pick items 1 through j, and we're going to assume that w is less than w of j. Okay? And what does it mean when little w is less than w sub j?
You can't take W.
You can't take an item j because there's not room for it in the backpack. So our strategy is going to be a choice you make when the second parameter is j is, do I take an item j or not? Well, we can't take an item j because there's not room for it. So how can we define this in terms of a simpler subproblem? If you've got capacity w and you're allowed to choose from items 1 through j, but item j doesn't fit, how can you reduce that to a simpler problem? Yeah. Right, k of w and j minus 1. We've reduced the problem to doing the best you can with the same capacity, but you're only allowed to choose items 1 through j minus 1. So you've had your chance to take an item j, it didn't work out. Now, what about here, where there is room for an item j in your knapsack?
Take J.
You can take a j, or you can not take a j, right? We don't know which is going to work out better. So we'll try both and see which way leads to the best solution. So we take the max of 2 things. So what's the 2 things we're taking the max of? What's the subproblem that corresponds to taking, what's the answer that corresponds to taking an item of item number J.
K of W minus W of J, comma J minus one.
I think that's right. So this is copied from above. This is the maximum value you can get if you choose not to take an item of type J. This is the best you can do if you do take an item of type J. You get the value for item J that you've stolen, plus the best you can do with the remaining capacity in the remaining items. So that just, it's a W recursive max. It just says there's two possibilities. Either you take something of item J, in that case, this is what you end up with, or you don't take an item of type J, in that case, that's what you end up with. You take the best. You see what's the best. So that can take a while to wrap your head around. But the real leap, the real creative leap, comes from that very first thing on the slide, deciding you need a two-parameter function. Yeah.
So when you're hashing this one, you have to hash the weight and
Yeah. If you're hashing it, you're hashing pairs, just like an edit distance. Your key would be the pair of W and J. Alright? A lot of uneasy looks. If you have an uneasy look, you're not the only one. Yeah?
So in the problem with repetition, we compared all the items at once. Here, we're only comparing one item at a time and choosing whether to take it or not.
Right. Because that's how we keep track of what items we're allowed to consider. See, otherwise, if you were allowed to consider all the items simultaneously, at each step, we would have to have some parameter that kept track of a set of things you're allowed to choose from. And rather than have a set of things you're allowed to choose from, we're doing it with this one parameter J here. It's the maximum index of the items you're allowed to choose from. So any solution of this is the recursion tree is only going to be 3 levels deep. At each level, you make a choice. Take item 3, do not take item 3. The next level is, do I take an item 2 or not? And that decision is made in 2 places. And then, do I take an item 1 or not? So the tree is shallow. Well, it depends on how big the table is. Okay, so once you've got that, it's just a matter of coding it up. So we can again view it as either the problem of filling in a table or the problem of just write this recursively and caching it. Rather than go through a complete solution, let me just ask you a couple questions. That green square I just lit up, which is at index, that corresponds to a 9-pound capacity, and you can choose items 1 through 3. What squares does it depend on? If you had to decide on the number you write in that green square, what 2 squares elsewhere in this table did you have to look at, according to this rule right here? Okay? You don't have to understand where this rule came from to answer the question. It's just basically a question about arrays.
The one directly below it.
The one directly below it, that corresponds to keeping W the same and subtracting 1 from J. And what's the other one? What would this one? What was that box?
2.
Okay, so it would be, we have to subtract the weight of item 3, which is 7, so we get to this column, which row?
2.
The second row, because it's J minus 1. So you get that. So that green box depends on those 2. Okay, so if you were filling this in, like we did the edit table, when you hit that green box, what you're doing is you're looking at the one number directly below, you're looking at the number over here and adding 13 to it, and then writing the larger of those up in the green box. Okay, what about here? What does that green box depend on?
The one directly below it.
Okay, the one directly below it, why is there not a second one?
Because there's not enough weight to take a
Right. You can't fit it. You have to subtract 7, the weight of number 3, from that green box, from 4, and that gets you off the scale. So we're in this situation, so it only depends on one thing. What does this green box depend on?
The one directly
Right? It always depends on the one below it, and possibly some number of hops to the left below. What about that one there? Yeah. So the one below it, and then the one below it, and then to the left by the way of that item 3. So now, of all the squares, which ones really matter? We want to compute the thing in the upper right-hand corner. What squares does it depend on?
Well, it won't depend on any of the other ones in row 3.
Well, let's be careful about that. What does that yellow one depend on? It depends on those two. Okay? And then that yellow one on the right on the second row depends on those two. And then if we just keep filling in, okay, that turns out to be all the squares that matter. If you if you made a recursive call up there for the upper right hand corner case with 11, 3, the only you would make recursive calls corresponding to these yellow boxes. It just turns out that's all the ones that matter. Okay? Because sometimes you do a double recursive call, sometimes you make this call, and so nothing else in the top row ever matters. So what does this say about, in this case, the relative value of doing building in a table, filling in a table, and then your answers in the upper right hand corner versus caching a recursive method? Which one wins here? Caching a recursive method. If you fill in the table, you end up writing numbers in all those white squares that do not matter. If you do it recursively, it basically automatically discovers the only things that matter. It just computes the yellow boxes. And so you end up with a faster solution. So that's another trade-off between the two. So it can be a little bit subtle sometimes. Okay? Yes?
Does this rely on the items being sorted by weight?
Say it again.
Does it rely on the items being sorted by weight?
Does it rely on the items being sorted by weight? No. No, they just have to be in some order. All right, let's take a break and we'll look at something different.
Does that problem actually, but in this specific instance of the problem, actually benefit from caching at all?
Yes. Yeah. That was the point I was making at the end there.
Well, so I know it benefits from recursing or filling in a table, but it didn't look like there was actually any overlap. So it didn't look like the caching actually benefited.
Well,
it didn't look like any of the yellow squares overlapped at all in that.
oh, I see what you're saying.
Yeah.
Oh, in this case, I don't know. I'd have to think about this a little bit harder. But you're right. It may be that we don't ever make the same recursive call twice. But it would be very data dependent.
Yeah.
So the other day I had this problem in a way, so
Hold on a second. I forgot to do this. Okay, now, we're not quite through with dynamic programming, but we will let it rest for now and come back to it on Tuesday. There are a few more things I want to say about trade-offs between filling in tables and using recursion. But in order to take a break, we will talk about another topic called linear programming. Okay, so linear programming is a general approach for solving optimization problems in which you can describe the constraints on the problem and the optimization criteria as linear inequalities or equalities. And so what you do is you express the problem as a linear program, and I'll show you what a linear program is. And step 2 is you solve a linear program using a standard algorithm. And we're going to spend some amount of time talking about the simplex algorithm, which is one of the algorithms for solving linear programs. But that's not going to be our main focus at all. We're going to focus on writing linear programs. And just like dynamic programming has its root probably in the 50s, linear programming, I think, it has its roots probably even earlier, and programming just had a different term in those days. So when you hear that we're going to be writing linear programs, it doesn't mean we'll be writing, Python or something. We'll be writing math. So here's an example. This is sort of a very simple linear program, and companies, use linear programs to try to optimize their, to optimize production lines, and this is sort of an abstraction of that sort of thing. It's a very simple example. So you got this chocolate company that makes 2 products, Matin and Nui, and these are the constraints they have. They can sell X boxes of Matin for a profit of $1 per box, and for Nui, it's $6 per box for each item they sell. So clearly, if there are no other constraints, they just want to forget about the cheap, the $1 profit per box and sell the more expensive. Okay? They got manufacturing limitations though. They can, well, I guess not manufacturing. They got sales problems. They can sell at most 200 boxes of Matin and 300 of Nui. They can produce at most 400 total boxes per day. And the question is, what should they do to maximize profit? Now you can probably solve that in your head. What should they do?
Max out your Nui.
Yeah, max out on the Nui. So make 300 boxes of Nui and sell it, and then use the 100. They can make 100 more boxes of the cheaper stuff. All right. So that's simple. But imagine if you have like hundreds of variables, not just X and Y, and thousands of constraints. And that's an industrial scale linear program. This is how you express it as linear program. You take your variables and you write linear constraints. Okay? So by linear, I mean you can add and multiply by scalars the variables, but you can't square them or take square roots or anything. Okay? So what's this constraint say?
X is for you have to sell these.
Right, you can't, what is the question? How many should we make?
You can't make
You can't make negative boxes. You can't make negative boxes. You can't make more than 200 of Matin. You can't make more than 300 boxes of Nui, and the total production can't be more than that. Okay, so those are the constraints. So a linear program consists of constraints, which are linear inequalities, and an objective function, which is a linear function they either try to maximize or minimize. So in this case, we're trying to maximize x plus 6y. So where'd that come from? Yeah?
Like the cost for like the Matin is $1 box, so that would correspond to like 1 times the x, which is x.
Right.
6 corresponds.
Right. So it comes from 1 and 2 up there. That's just the profit. You're trying to maximize the amount of profit subject to those constraints. So that's a linear program. Now we have to solve linear program. And this is different from any other thing we've studied in this class. Normally at this point I'd say, okay, we need an algorithm to solve linear programs. Let's solve linear programming algorithms. Instead, we're just going to use one. So I'm using LPSolve, which is freely available. There are lots of them available. But you can just, and this is written, this is the linear program up there written in the form design. This is just the form that's parsed by LPSOL. So it wants to see the objective function first, followed by a semicolon. You put max within at the beginning, and then the constraints. And students, all the time, when I say, write the linear program, they want to write 6 times y, 6 star y, as if they're writing Java or something. Don't do that. Think about the way you write in math class. So linear program, we just take that, copy and paste it in. And I've got LPSOL running right here. So there's LPSOL, and you may not be able to see it in the back, but I have, that's just the program copied in. I click run, I guess, solve. And then you have to look on the result pane, and it tells you that you should sell 100 boxes of X, 300 of Y, and the objective, the maximum value for the objective function is 300. Okay. So that's, in a nutshell, that's dynamic programming. So we're going to play around with dynamic programming. We're going to see that, it works for things other than boxes of chocolate. And in fact, you can use it to solve algorithms you might not think of as, to solve problems you might not think of as the kind you would describe with a linear program. And it turns out that any optimization problem that can be solved in polynomial time by any algorithm can be solved in polynomial time by expressing it as a linear program. So you could take Dijkstra's algorithm. You could take the problem of finding shortest paths in a graph, and rather than use Dijkstra's algorithm, you could describe that problem. You could describe the graph and the problem as a linear program and solve it using LPSOL. Now, it's not going to be necessarily as fast. It'll still be polynomial time, but it won't necessarily be as fast as a specialized Dijkstra's algorithm. But you can describe lots of things as linear programs. We have time, I'll show you an example today. All right, I want to give you an idea about how linear programs are solved. So what I've done here is I've graphed the constraints. And the pink area is the area that, the points in the pink area satisfy all the constraints. So I've got x greater than or equal to 0. I've got y greater than or equal to 0. I've got x less than or equal to 200. So that's this line. I have y less than or equal to 300. That line. And then I've got this. That's this line. So that's my region. And there's the objective function. And we could go around and start picking points. And we could say, what's the value of the objective function right here? And what's the value right here and right here? And the job is to find where it's maximum. And of course, there are an infinite number of points to choose from. We're dealing with real numbers here, not integers. And so it looked kind of daunting to figure out where the max will occur. But it turns out it's not that hard. Let me show you why. Now that pink area is called the feasible region. So that's a little bit of terminology for you. So what I've done here is I have just graphed x plus 6y equals 180. I just picked 180 out of the thin air. So what can you say about all the points on this line in the feasible region? What's the value of the objective function along this line?
180.
It's 180. Okay? Now, what would happen if I changed the 180 to 190? What would the line look like? It would be a little bit higher. Those lines, the points on those lines give us a slightly higher value of the objective function. If I keep increasing, 180, 190, on up to 1,000 or whatever, the line gets higher and higher. So let's see what happens. Watch what happens as I basically move the line up, which corresponds to increasing, x plus y equals 180 to x plus y equals something else. Okay? Then it leaves the feasible region. Okay? Now, where is the very last time that the line intersects the feasible region?
There.
Right at that corner. Okay? So that corner, we know that as the line goes up, the objective function gets larger and larger. The value of x plus 6y gets larger and larger. So that is the largest value that the objective function could have before it exits the feasible region, which means that the optimal answer is the one at that corner, which is 100, 300. Now, were we just lucky that it exited at a corner?
Maybe.
Okay? Can you think of a way, imagine this thing being sloped in a different way. Can you imagine a straight line that when you animate it is not going to exit at a corner, where the last point it touches won't be a corner? Yeah?
Maximize x plus y.
Okay, maximize x plus y, in which case we've got a line going this way. And it will exit, the last thing it will touch is this line right here. And then it will exit. But at that last instant, it touched 2 corners. Okay?
Didn't touch the whole line.
It touches the whole line, but it's also touching the 2 corners. That's the point. So it will, the last thing it may touch a bunch of points at the last instant, but at least one of those points will be a corner. So what does that tell you about if you had to go find the place where the objective function is the largest? Do you have to look at every point in the feasible region? Not even the boundaries. Where do you have to look for this value? Just the corners. Okay? Now, if you have concave feasible regions, or feasible regions where the edges are curved, this wouldn't work. Why do you not have concave or curved regions? It's all linear. So the simplex method and related methods, they're basically checking at corners. Check all, one way to think about it is check all the corners and see which is maximal. The problem is you can have too many corners that it's not efficient enough to look at every corner. So they're smarter than that. What happens if we add more variables? What if we have 3 variables? So it's x, y, and z.
It's a 3-dimensional graph.
Right. Now the feasible region is not a 2-dimensional thing. It's a 3-dimensional solid, a polyhedron. And what's the objective function in that case if you graph it? It's a plane. And again, if you animate it, it's going to exit it'll exit the polyhedron at a point where the plane is intersecting the corner. So the maximal value will be at a corner. Now what if you go to four variables, and suddenly you're talking about a 4-dimensional solid and a 3-dimensional solid that represents the objective function. Right? So I'm all out of visualizations to that point. But the mathematics still work out. You're still looking for, you still need, the objective function will be maximal at whatever you call a corner in 4-dimensional space. Maybe it's still called a corner, I'm not sure. Okay, so it works for n dimensions. And the algorithm's just smart about not having to look at every corner. All right, and that's what I just said. And that's what I just said. Okay, here's another problem. So this is a 3-dimensional problem. So now we're adding loops. I guess that's maybe how that's pronounced. At a different profit point, $13 per box. And there are other constraints, like number of minutes you can package them after you produced them and so on. And that'll lead to a different linear program. So what are some of the constraints we'll see? What constraints do you get out of, well, first of all, what's the objective function? X plus 6y plus 13z. And then you've got x, y, and z have to be greater than or equal to 0. What else do you have? What does number 4 give you?
X is less than 200, y.
All right. X is less than 200, less than or equal to 200. Y is less than or equal to 300. X plus y plus z is less than or equal to 400. And y plus 3z is less than or equal to 600. So those are our constraints. So there's the linear program, and we could run that through LPSolve and get a solution there as well. But here is a problem that's very different. So this is an example of a network flow problem, and there's specialized algorithms for solving these on graphs, but we're going to solve it using a linear program. The idea is we've got pipelines that lead from cities to cities. They're directional. So example, there's a pipeline from S to A. And we want to pump oil from S to T, as much oil as we can. We want to ship as much oil over the network as we can. But there are constraints. We can only send 4 units per hour to C, from S to C. We can only send 3 units per hour over this one here. We can only send 5 units per hour over that. So we can get as much oil, we're sucking oil out of the ground here, so we can take as much oil out of the ground as we want. And we're shipping it away here. So we can accept as much as possible. But we want to figure out how do we get the most oil possible. But there's another constraint other than the individual pipeline constraints. Can you see it? And I'll give you a hint. There's no storage capacity at any of these interior nodes. So there's no way to store excess oil at C. So what constraints does that add? Yeah?
You have bottlenecks at your minimum pipes.
Say that again.
So like D to T or A to D, since those are less than S to A, you can only pump out really 2.
Okay, well, I think you're getting at it. Let's look at A up there. Could you use this line and this line to capacity and send 13 units per hour up to A?
No.
Why?
It can only send out 2.
A can only send out 2. So the amount of oil that's coming into a node has to equal the amount going out. And you get this. So we have to express those constraints. So to write that as a linear program, first we need to pick some variables. And what we're trying to find out is how much oil do we send out of each pipeline per hour. So what's the natural choice for variables? Well, not the vertices. The lines, the edges is what we care about. Because we want to ask, how many units per hour do we send out on the edge from S to A? How many do we send out from S to B? How do we end up from S to C? So we need constraints of that form. So let's make a variable for each edge, and we'll call it after its endpoints. So SA is the edge from S to A. AD is the edge from A to B. Okay. Now what constraints can we put on a variable? So what's the constraint that says you can't ship negative oil in the pipeline?
Each one has to be greater than or equal to
Right. So SA greater than 0. And the same thing for each edge. Okay? What's an upper constraint you can put on each edge?
the number of things.
Right, so SA is less than or equal to 3. LC is less than or equal to 4. Okay? How do you express a constraint that, say, the oil into vertex A has to equal the oil out the vertex A?
I don't know.
Okay? Who knows? How can we write a constraint that says oil in has to equal oil out? Yeah.
SA plus BA equals AD.
Exactly. Okay? So you can have equalities as well. There's sort of a union of 2 inequalities. The intersection of 2 inequalities. So anyway, SA plus BA has to equal AD. Oil in must equal oil out.
You can't be less.
No, can't be less, can't be more. Because we've got no way to store. Well, the oil in can't be less because then you can't, you're not going to be able to ship that much out. Oh, wait. Yeah, you're right. No. The oil in has to be the amount out. Well, the variable is representing the amount of capacity we're using. And any oil that comes into A has to go out right away. It can't accumulate. Yeah.
Really what he's saying is that you can type 2 out, but if you only have 1, then you have to type 1 out. Really, so.
Right, if you're only getting one unit per hour in, you can't ship 2 out, you don't have the oil to ship. Okay, what's the objective function? We're trying to maximize the amount of oil that we get from S to T. So we need some expression that captures the amount of oil reaching T.
Or if we just maximize ET and DT.
Yeah, we maximize ET plus DT. That's the amount of oil going in. Or you could also maximize oil going out of this. Either way it works. So you do all that. This is a preview of the solution, by the way. So there's the original problem. This shows how much of each edge you end up using. So this is the solution you can obtain. And you see, you can't do any better than this because you're using the full capacity into T. We're getting 7 units an hour into T, so that's, we're not going to be able to do better than that. And here's a linear program. So you do that. These are all your constraints. We talked about all of them. So there's one of these for each edge. There's one of these for each edge. And then there's one of these for each internal vertex. This one is written to maximize the oil out of S, which is going to be the same as the oil into T. And you feed that into an LP solve, and what you get out is the numbers on the bottom line. The values of the variables that come out are going to be these values right here. So there, we don't even have to learn any algorithms for maximal flow. We can express it as a linear program and solve it. Yeah, let's end there. We'll look more into this next time.